Hello, Internet. So, we are going to do level 20, which is denial, and we're on a roll this weekend. We're going to do 2 in a weekend, which is great because we're almost done. We have 6 more, and we're finished. So, this challenge is really very similar to King. So, we have level 9, which is King, and that's the one that we did. And in the challenge, there is an explanation, per usual, so let's read it. This is simple. Now, this is a simple wallet that drips funds over time. You can withdraw the funds slowly by becoming the withdrawing partner. If you can deny the owner from withdrawing funds when they call withdrawal, then you win this level. There's a specific mention here in the parentheses of basically stating that whilst the contract still has funds, the transaction is of 1 million gas or less. This specificity here around 1 million gas or less isn't something that I've actually seen discussed or highlighted in the solutions that I've come across, and I've come across 3 different solutions, or two different solutions that you can do this with. So I wouldn't be too concerned about this piece, partly due to the fact that you can solve it without it. But if you can find a specific solution that kind of urges or satisfies that need, then kudos to you. With that being stated, as we said here, our goal is basically to ensure that we can deny the owner from withdrawing funds. That's basically it. That's our goal. And in this contract, we'll talk through that in a second. Before I jump into the contract, some of the resources that I found useful, first of which was this was the first solution that I came across, which is one of the methods you can do this. One method is doing it via error handling, and the other one is basically doing a reentrancy or a while infinite loop into the contract. And the other resources that I came across, this one is the solution that I use because it's the solution that I found that worked, because the first one that I just showed you had some issues working, and I found actually a stack exchange conversation happening back and forth, assuming that it was not possible to solve the solution due to the fact that there's been some updates within the EVM or in the compiler specifically to what we're trying to utilize. And the last one is this video here, which is, I think this is the last video that he's put together for the series. So from now on, we're on our own, which is always exciting. And in this solution, he basically used the same solution that I shared in the first blog that I showed you with error handling. So those are the resources that we used to understand this. Like I said, it's similar to King. And here's a dope picture that has nothing to do with the challenge, but I wanted to call it out because it's great. And this is referring to DALL-E 2. So if you've not researched DALL-E 2, I'll drop this link in the chat because it's unrelated to blockchain, but it's an accomplishment that OpenAI accomplished with basically running 640 million images through a model to actually generate images like this via text. So unrelated, but you should check it out. All right. And before we get into this, there are a few things to note about the challenge itself. So when trying to compile the target code, there's some adjustments you had to make if you wanted to compile to 8.0 or above. And then also in addition to that, this is the post I was referring to on Stack Exchange. It basically asks, is the denial challenge impossible to solve now due to the fact that there's been updates within the compiler? The consensus that they came to, I think, was that it was, but I don't think many of them came across the solution that I came across, this one here that has an alternative solution, which is the infinite loop here. So you can read through that and kind of get a gist of what concerns they had there. And the updates that I had to make we'll discuss later on. We'll skip that for now. Groovy. All right, let's go to the code. So here we have our target. Now in our target, you can see it's being compiled, and it's being compiled in 6.0, but if you wanted, like I said, to update it to 8.0 within Remix, you would have to obviously change this to 8.0. Floating points, no bueno for production. We've talked about that many times. We're going to import SafeMath, and remember that if you're going to import SafeMath and you're going to use 8.0 for your compiler version, you're going to want to add an additional slash in here, and you're going to want to add utils. So that's going to look something like this. So when you try to compile this in Solidity or in Remix, you're going to want to include this piece here. Next, we have a contract called denial. We have a few state variables being established. So the first one is we're going to import SafeMath so we can use it later on down here. We are going to establish an address called partner, and that's going to represent us, so we can actually drip feed money outside of the contract to ourselves, and that's going to be representing our address. There's another address here that's associated to the owner, so the person that deploys this contract in the first place. And you can see their address looks like it starts with these four first few characters. We have a uint that isn't explicitly stated around the type of uint, so this is going to automatically default to 256. And this is going to be the time at which this was withdrawn. Down here we have a mapping, so this mapping is going to basically represent the balance that the partner has. So we're going to have our partner address and the associated balance that they have that they've withdrawn from the contract. And then we're going to go to our function. Now, this function here is basically going to set the partner. So we have to call this first when we're running our exploit because we need to be a partner first so we can actually withdraw funds from the contract. So we'll call this by putting our address in here, and then it's going to then associate us to this mapping here, and also we'll have our address here, so we have something set up there. And now this below here, this is where all the magic happens. This is the function that we care most about, which is the withdrawal. Now in here, there's some comments that came with the target, so you'll see within the challenge on Ethernaut that there's some comments in there highlighting stuff and some stuff I've added. So this is included, so it basically states that the purpose of this function is to withdraw 1% to the recipient and then 1% to the owner. The recipient's going to be your partner here. That's going to be us. And then below we have our function called withdraw. We have a few things happening here. So first we're going to divide our balance by 100. Then we're going to then give it to this address, which is going to be us, the owner, or not the owner, but the partner. And it's going to show you the amount that's going to be sent to that partner. One thing to point out here is you can see there's a div of 100. My assumption is that it's correlated to this 1%. So we want to divide whatever that is so we can get the 1% to both parties involved. Here is this is the issue. This is what we're gonna attack right here. But I'll explain what it is briefly, and then we'll kind of complete everything else, and we'll come back to highlight specifically what we're going to attack. So this is the partner we're gonna call, and the video that blockchain developer dude that I'll link below that did the ETH series, he spends like 40 minutes talking through the difference between call, send, and transfer, which are the different methods of actually sending money back and forth between contracts. I'm not going to do that because he did it, so go feel free to watch that. In a nutshell, transfer and send are methods that a lot of people shy away from today, or should shy away from today, because there are gas limitations on what can be sent when you're sending a transaction or interacting with another function. Instead, you should use call, and the reason you can do that is because you can actually customize the amount of gas you send. The reason that's relevant is because the opcodes and the associated gas with those opcodes is changing over time. So in 5-10 years down the road, maybe those gas limitations would hinder your ability to interact with other functions. I've talked about this in previous challenges as well and highlighted it specifically on, I think it's a consensus blog. So if it doesn't resonate here, check that out. So here we have a variation of sending or interacting with another function. In our case, we're sending gas or sending Ether. So we're basically going to say we want to send a certain amount of Ether to the partner. And you can see we have our value. It's going to call out the amount that we established here. And then we have this funky looking thing what's going on here. So what this is representing is saying that we're going to send this to a contract where we don't necessarily know the function name. Because remember, when you interact with another contract, you need to know what the function name is. You need to ABI encode that so you can interact, I think, with the 4 first bytes of the hashed function. But if you don't know it, then you just send it like this, and then it's going to interact with whatever, usually I think it's receive or fallback functions. That are the 2 functions that you can hit within a contract where you don't necessarily know the function name. That's what's going to happen here is we're going to hit a fallback that we've set up. Additionally, with this is that this low-level call, we've not specified the amount of gas we want to send with this transaction, or we have not set a limit for the gas amount. With that being stated, if we've not set a limit, that means we're sending it all. So we're going to send an interaction with the contract. We're going to say, when we do this, I want to give you all the remaining gas. And you can execute as much as you need or as much as you want before I continue through my function. And that's what we're going to exploit here. Because what we're trying to do is we're trying to prevent, get this out of here, we're trying to prevent this owner from doing their transfer. Remember, that's what the challenge was, is prevent the owner from actually withdrawing any funds and preventing that by basically taking all the gas. And what they're doing here is they're using a transfer. So if we used a transfer here, we wouldn't have been able to do this exploit. But since they used call, that's allowing us to do this. But they're using transfer instead. And this transfer is basically saying I want to transfer the amount to send, which is going to be the same that we sent to ourselves. And then after that, we're going to go here. We're going to say time last withdrawn. So this is going to be now. Remember that if this is an 8.0, we're going to want to change this to block.timestamp. So b.timestamp timestamp, and it's going to be block.timestamp, but I didn't write it all out, and my writing here is unreadable, but that's block.timestamp and 8.0. And then below here, we're going to basically do an effect. So we're going to add the amount that we've withdrawn and then tack it on to our partner. So we're going to say this is the amount that we sent. We're going to add this to their balance that they've withdrawn in the partner, and that's going to be correlated to our mapping here. So withdrawn partner balance, and that's going to increment that balance that we've withdrawn. They have a basic receive function, which is the other method. So remember how I talked about this piece here? Well, like I said, it calls out to it interacts with two functions if you don't necessarily specify the function name, one of which is receive, and the other one is fallback. Here they've set this up so if somebody wants to deposit funds into their contract, they're allowed via this receive function here. And then we have a convenience function here that's basically checking the contract balance. So it's a public view returns, so that means that it's not going to really do much interaction. It's just going to read information and not write it. And we're going to return a uint, which is going to be the balance of the contract currently for this contract. So that is the target, and those are some of the things we're going to consider here in attack. With that being stated, I have our attack contract here as well, two variations of it, and I guess I can explain both, and I'll just run one because I think the one is the only one that works. And here I have the two solutions in the notes. So one is about error handling, and the other one is about an infinite loop. So the error handling one is one that you'll see in a lot of the explanations. So you'll see it in this explanation here from Roga. You'll see it in the other ones that I've called out, such as the video as well as the other blog that I shared with you, the first one I came across. And specifically in those explanations, they're talking about there's different methods of error handling. And there's a simple table here that shows that and what those error handling methods are. And when looking at this, the most important thing to point out here is that revert and require, they revert all the state changes. It actually refunds the remaining gas to the call. That's what those two do, in a nutshell, if a condition is not met. There's also a throw mechanism here, but this is deprecated, you can see, as of 4.3 and removed from 5, so we can kind of just ignore this piece here for now. But with that being stated, there's also another really good video I wanted to point out that explains those different methods of error handling from our favorite smart contract programmer YouTuber dude that does a great job of explaining each one of those and the new custom error handling that you can do with an 8.0. So check that out to understand more about different types of error handling. But for our understanding, really what we need to understand at a high level is that with an error handling, these two revert the state, and they also return the remaining gas. But we're going to leverage assert in our attack. Reason being is that if you leverage assert, then it actually depletes all the gas. It doesn't actually refund the remaining gas. And if it's going to deplete all the gas, that means that we're not going to be able to continue through our contract as we were trying to do earlier and preventing the owner from withdrawing. So this is going to be key for us for this assertion one. Additionally, it actually doesn't revert the state either in assert, and reason it doesn't do that, and you can see this within, if you read the documentation, I'll link this in there as well, it calls it out specifically in the documentation stating that low-level functions such as call, delegate, and static call, instead of actually reverting the state and doing kind of an exception of throwing bubbling up, you can see it calling here, bubble up. Instead, we're going to return a false value or a true value. And the false value you're going to return isn't necessarily going to revert the state. So that means that we can use this specific error handling to continue through this contract and this attack. Because if it did revert the state, then basically everything we've did up to this point here would be reverted and we wouldn't be able to continue. But since it's just going to return a false, we're okay with that because it's going to continue through the function, or it's not going to continue through the function because we're going to deplete the gas, but it's not going to revert the state either. So it's kind of a happy medium for us. All right, that's that piece there. This is the same explanation I just gave just in text, and same explanation here as well. So we're good there. Cool. So we'll go to this code here to explain it briefly, and then we'll explain the code above. So this is the solution that you'll see in many different contracts. And what they're going to do here is basically, we have our compiling, we're going to import denial so we can interact with the contract and also initiate it. We have our contract, we're going to initiate the contract here into a state variable called denial. Our constructor is basically going to set up our target contract, so this is the target that we care about. We're going to put that address in there. It's a payable contract, which is important. And we can see that we're going to initiate that and put it into another variable here called denial contract. So we can call the method later on. This function here is the initiate attack, and this is something that we'll do via the console instead of inside of the contract for our approach. But what we're going to do here is we're just going to set the withdrawal partner so we can actually be on the balance and we exist so we can withdraw the funds. So we have to initiate ourselves in the balance sheet within that contract so we can actually start taking money. And then you can see this is calling out this address and it's pulling the method from the variable we've set up here. And then this is where the attack occurs, right? So we have a fallback, external payable, which is important. And this is the point that I made earlier, where remember we had the parentheses and the quotes. When this calls, remember I said it goes out to two places, right? So it either goes to the receive or the fallback. So if we set the fallback here, that's what's going to hit because we have no function that it's called specifically to hit. And when it does that, it's immediately going to an assert, and that immediately is going to kick out a false. And when it does that, you can see I put a comment here that it's going to consume all the gas before it moves on to the owner to withdraw the funds. And if we do that, that means we've beat the game. We've done exactly what it asked us to do. So that's one approach, which is error handling and focusing on the different types of error handling that you can set up and how you can deplete the gas there. The approach that we're going to use was provided via the this block here, which is calling out another method of doing this attack, which is in an infinite loop and a while loop, which are just going to consume the gas that way as well. And here it's super duper simple, and I love just how simple it is, where it's so simple that I messed up this text here. Let's do that so it looks like that. All right, so we have our compiler version, and also when we run this in Remix, we're going to compile it to 6.0 because of the previous issue that I talked about in the Stack Exchange post. So we're going to compile it to 6.0. We have our contract, it's called attack, and here we just have one thing, and that's the fallback. It's going to hit the it's going to hit our contract when we call it, and it's going to be while true, continue. Just keep doing whatever infinitely. Just keep going, keep going, keep going. When it does that, as it keeps infinitely going through this this loop, because it's always going to be true because we stated it to be true, and there's no changes happening inside the loop, we're going to deplete all the gas, and we're going to win the challenge that way as well. So with that being stated, let's go to our notes to make sure we didn't miss anything. That's the fix, so we'll come to that later. All right, so that's that. Here's our remix setup. All right, so in here you can see that when I compiled this, I compiled it to 6.0 when I saved this, and we got no errors, which is great. We're going to inject Web3. We're going to deploy our attack contract. And once we deploy it, let's go back to here, and let's jump into our console, and let's clear that up so it's not so crazy. So let's do contract ABI to see what we have in our ABI. And this is basically everything that is within here in some way, shape, or form, because we're not inheriting other contracts, so there's no additional stuff in there. I'm just curious. I've not done this yet, but let's just see what's actually in the balance. Okay, so we can see there's some money in here. And now what we need to do is we need to contract. I don't know why it's not doing that. Why isn't auto completing for me, internet? Await contract dot set with. All right, so now that we have deployed our attack contract here, which is successful, you can see the little green dot, we can see our contract here. What we need to do now is we need to copy the address from this contract and set it up so it's within the partner address, and it has its own mapping here, so we can actually start withdrawing funds. So to do that, we're going to call the set with draw partner, which is what we've talked about here, and we're going to put in that address of our contract that we've just deployed, which is 5FE. 5FE is the same. So then we'll do enter here, and we'll deploy that. So once this completes, that's going to set us up as an individual that can actually run this attack. And I think once we set that up, it should potentially automatically work. But let's check the solution just in case. Yeah, it should automatically work. The reason being is when we set this up initially, it's going to initially call out to the contract to put it inside of this setup. And when we do that, it's immediately going to hit our fallback, and it's going to deplete all the gas from the contract. So ideally, if we submit this instance, we should have won. And there you go, internet. Congratulations, you beat the level. In their explanation here, they're going to talk through a lot of what I've already discussed and how they basically point out the fact that You can specify a fixed gas amount with the call piece, which is important, and that's what they should have done in the target contract, but they didn't. They just sent all the gas for us to deplete ourselves. Also, they talk about the check, effect, interact, and that is hopefully going to leak out to the documentation. Cool, it does. But that's where the fix comes into play. So the two fixes that I wanted to call out here, and the two things I wanted to really bring your attention to is this is something we've talked about a million times, and we'll probably continue to talk about throughout all of these levels, is the check, effect, interact pattern. The reason we're going to call that out is because if you look at the specific target function that we care about, which is withdrawal, we can see that all of the functions they have here, they're set up in the incorrect order. Reason being is there is no check. There's no check happening here when it's supposed to be check, effect, interact. What's happening is we're going to immediately interact first. So that's going to be the first one. Then we're going to effect second, and then there is no check. Because here we can see that we're going to effect, so we're going to basically set up the amount here. There's some effect happening here. We're then going to interact, which is the first piece. So actually this isn't really a check. I think this is an effect. I don't know. They're updating a variable, so I guess it's an effect. And then these are the interact pieces. So we're going to interact with our partner and our owner. And then we're going to update some stuff here. And we're going to then add our balance again, so this is an effect. So there is no check here, and that's one of the major issues here is with that pattern that they've coded out. They should have set something up there to check that. And then the additional piece is something we've already talked about a few times, which is ensuring that the low-level call, when you use the low-level call, you should ensure that there is a gas limit set there, so someone can't just automatically deplete all the gas from it. And with that being stated, Internet, we have officially completed level denial. We're going to move on to shop, and we're almost done. We're almost there. I'll see you on the next level.